rolling, there are two basic components. First is the material which is being rolled, and second, the rollers which rolls the material which performs the rolling operation. So let's say a material approaches two rolls. It approaches with a velocity, its own velocity which is provided by conveyor belts, and then under the influence of the rollers, it leaves with a separate velocity. And the rollers also possess their own velocity, which is called the surface velocity. And this surface velocity is nothing but the tangential velocity of the rollers. There is no external force required to pull the material out of the rolls. It is done simply by friction. Now, let's suppose H0 is the initial thickness of the work. H1 is the final thickness. V0 is the velocity of approach of the work, and V1 is the velocity of work after rolling, and V is the surface velocity of the rollers. Now in this whole process, there is bound to happen some unbalanced forces. So to counter those unbalanced forces, we need to provide similar velocity of top and the bottom roller. And since both the rollers are rotating in opposite direction, the top roller is rotating in anti-clockwise, whereas the bottom roller is rotating in clockwise fashion. So ultimately, the material that is being rolled in between, that is being worked in between, because it's a mechanical working process, it's a metal forming process. So we are working on material, we are working on metal. So if the metal is getting worked in between, it will automatically pulled outside due to force of friction. Now, right now we are trying to avoid certain unbalanced forces which are being generated. And we have seen the velocity of the two rollers are same for the same cause. Or we can say pi dn of the top is equal to pi dn of the bottom. Now again, to avoid unbalanced forces, the diameters of the top and the bottom rollers should also be same. And hence, in essence, we understand that the revolution per minute for the top and the bottom roller should also comes to be same. So finally we can say these three parameters, the velocity, the tangential or the surface velocity of the rollers, as well as diameter and the revolution of the rollers, remain same in order to avoid unbalanced forces. Now, in rolling operations, it's not always that the height of the work is getting reduced. Sometimes the width is also gets reduced. As you can see here, B0 is the initial width and B1 is the final width. L0 can be termed as the initial length of the work, and L1 would be the final length of the work. Here L0 and L1 are not specified, but you can get idea when this particular work is completely out of the picture, completely out of the rolling process, a different length will definitely be there. Now here comes a term that is called angle of bite. This angle of bite is actually an angle subtended by the center of the rollers over the complete deformation zone. That means up to which the deformation is taking place, deformation of the work material is taking place. Now, there are certain assumptions in understanding the rolling mechanism. First, the volume of the work material remains constant. These are the ideal conditions. In practical sense, it's not at all possible, because due to scale formation, as far as hot rolling is concerned, scale formation, oxide layer generation will be there, and scale formation will be there, and due to the scale formation, the volume will be considerably reduced. But we are assuming, for the sake of understanding the process, the volume is constant. We are taking an ideal condition. Also, the width remains constant. Now, the volume is constant, so we can write the initial and final volume is equal, or H naught B naught L naught is equal to H1 B1 L1. Now the width is also constant, it's also assumed constant, so we will get H naught by H1 is equal to L naught by L1. Now the third assumption is that the flow rate is also constant. That means A into V, the product of cross-section area and the velocity of the work material, is constant. Or we can write A naught V naught is equal to A1 V1, or H naught B naught, which is the area of cross-section, into V naught is equal to H1 P1 into V1. This H naught, this H1, this 0 sign is for the entry position and 1 sign is for your leaving position. So from this we get H naught by H1 is equal to V1 by V naught, and it is always greater than 1. So we can regard that the velocity at the exit, that means when the material has been rolled, the velocity is higher than the entry. The velocity of the exit of the work material is higher, always higher than the velocity at which the work material enters the rolls. The fourth assumption is that no extended push or pull is required. The work is simply pulled because of friction between the rollers. Or we can say the surface velocity is also greater than the entry velocity of the work material, and this is a very required condition to pull the work. Otherwise, the work will be stuck between the rollers and we will get a breakdown of the rolling mill. So comparing the previous condition and this condition, we have the velocity at the exit as the topmost velocity is the highest velocity, followed by the surface velocity or the tangential velocity of the rollers, followed by the entry velocity of the work material.